Oh, all right. Hello, everyone. Welcome. Oh, not sure if it started or not. All right. So, yes, hello, everyone. Welcome back to the course. Welcome to the next lecture. All right. So, let's see. So, last time we finished off the first stage of the compiler. We finished off with parsing. And now we're into what's sometimes known as the middle end of the compiler, or the context-sensitive analysis, right? So in the parsing phase, we had the compiler figure out the structure of the code, how the code is nested. Different parts of the code are nested within other parts. And in the context-sensitive analysis, we're going to start looking at what things in the code mean, and specifically named things like classes and methods and variables and those kinds of things. Okay, and so I have an example on the board here, but ignore this stuff for now, and let's just look over here. So we're going to start with name resolution. Really, the sort of two big topics in context-sensitive analysis are name resolution and type checking, and the two are usually discussed separately. But in most languages, or most modern programming languages, you actually have to do name resolution and type checking together. So for us, we're going to have two assignments on these topics, assignments 2 and 3. But I'm going to talk about name resolution first, and at some point I'll tell you, how the two are going to be interleaved in the actual implementation. Okay, so just as a warm-up for name resolution, right? So okay, so you've parsed your Java program or your JUICE program. And now somewhere in, somewhere within your program, you have some code that looks like this. So A, B, C, D are some names of things. And, in the middle of some expression, you see, A.B.C. .D. And the question is, what does this mean, right? And where do I find the A and the B and the C and the D? What do these names actually refer to? And maybe just for the sake of example, let's say after the D there's some brackets, and so maybe if you see this in a Java program, you probably think, okay, well, that's a method call. Okay, so all right, so D is probably the name of some method, right? And so your compiler would look around your program to try to find a method named D and hopefully find the right one. So what about C and B and A? And yeah, let's try this. So anyone, can anyone tell me, where I should look for A, B, and C? What they might be? What can A be? Okay. So this usually works better when we're in person, right? But we have the chat, package names, class names. Okay. So yes. So all right. So one thing that we could have here is that maybe C is a static field, right, in some class named B. So B, little b is the name of some class, and sort of typically as a convention, we use capital letters for class names, but there's no requirement that forces that, and so it could be a class with a lowercase name, and then A would be the name of a package. All right. So I have a package named A, and inside it there's a class B, and that class B has a static field C. So you say B.C, and then That static field is a reference to some object, and that object has a method named D, and you're calling that method on that object. Okay. On the same theme, A and B could both be packages. They could be like B could be a subpackage of A, and then C could be the class name, and D could be a static method inside that class. So this, these are, I guess, two possibilities already, but they're not the ones that I would have thought of first. So my sort of first thought would be, well, I mean, it says A, so A is probably a local variable, and then it's a local variable that has that holds a reference to some object, and that object has a field B, and that field is a reference to some other object, and it has a field C, and then the D is the name of some method. Okay, and I mean, the compiler needs to not only know, is it a field, is it a method, but it needs to know which field and which method it is. Okay, so anyway, so the whole point of name resolution is to look at uses of names, so places in your program where you write a name like A, B, C, or D, or whatever identifier, and name resolution has to figure out its meaning, what actual concept that name refers to, which specific variable it designates. Okay, and I've got a question, Colby. Yeah, so A, B, and C could be classes. Yes, in fact, they could be. So A could be the name of a class, and B could be a nested class that's nested inside class A, and then C could be a class that's nested inside B, and so on. So that's also a possibility. So there's lots of, when you see A.B.C.D in your Java program, there's lots of things that could mean, and it's not obvious what thing it's referring to. Right, so they could be classes. Oh, right, so they could be classes in Java. They cannot be classes in Juice because in Juice we disallow nested classes. And part of the reason that we disallow them in Juice is that they make name resolution, even more messy and complicated than it is, than it already is, even in Juice. Okay. Yeah. So good question. If there's other questions, please put them in the chat. Okay. And so just as a little bit more warm up, okay. So this was one crazy example where something that looks simple can mean different things. And I have a sort of a bigger example, and so here's some Java code, and let me get another color here. And so what I've done is I've color-coded declarations in blue and uses in red, right? And so a declaration is what introduces some concept like a class or a variable, or I guess in this case it's a field. So a field, another field, a method, or a parameter, or a variable here. So a declaration introduces that concept, and a use is a reference to that concept. It's you use the name to mean that concept. So I have declarations in blue and uses in red. And the idea of name resolution is to connect each use to a declaration or to the identity of the concept that we're referencing. So I can write that here, right? So the whole point is connect uses to declarations. Okay. So, all right. this might seem trivial, but it's going to get non-trivial later, right? So we as the compiler, we go through the program and we see a use X. And one more thing, so how do we know that it's a use and not a declaration? So we know that from the syntax. So from the place where this identifier appears in the grammar, right? So when you go through your grammar of Juice or of Java, there are lots of different places where a name or an identifier could appear. And some of those places in the grammar are declarations, like right after you create a class, or when you're declaring a field, and others are uses. And so you have to look at your grammar and decide, okay, which things are really uses, and then for each use, your compiler is going to have to link it to the right declaration. Okay, so if we're doing this just by hand, right? We're not the compiler. We just are using our own knowledge of Java. So what actual concept does this X refer to? Well, generally we're going from the occurrence outwards. And so the closest X here is this X over here. So we would link this use of X to this declaration of X here. Okay, here, this use of Y, I guess now it's not 100% obvious because there's a Y here, but there's also a Y here. But this parameter Y is closer to where we're using it, right? It's within this method, and so we're going to link this use of Y to this declaration of Y and not this declaration of Y. Okay, so maybe you're thinking, okay, this is easy, right? These are trivial, but let's see some more examples here. So one thing that we see here is I declare class B, and I say that the class B extends class A. And, B here is a declaration. I'm saying, okay, here's the new concept class B, but A is a use, right? There could be lots of classes that extend the same class A. So for the A, we're trying to figure out which class A we're extending, right? And in this example, maybe it's obvious that we're extending this class A, but in general, you could have lots of different packages, and you could have a bunch of different classes all named A, in a bunch of different packages. And so even figuring out which class you extend requires some sort of non-trivial name resolution. Okay, so moving on, I have this field declaration. So it's declaring a new field called Z, but the field declaration itself has a use in it string, right? When you say that the field Z is of type string, what is string? Well, string is actually some class declared in the library. So I need a declaration for Java Lang string. Okay, and it's actually the class Java Lang string. And so we need some magic to tell the compiler that any class that's in the Java Lang package can be used without specifying the package name. All right, but this kind of a use of a name from the library is why, starting from assignment 2, we're going to no longer compile one file at a time, but we're going to compile the whole program, which means the entire standard library. And I think I mentioned this at the very beginning of the course, but the Java standard library is huge. And it uses some features that are not Juice features, right? Because it's Java. So for the purpose of the course, I'm providing a a tiny little juice standard library that has the most important things out of the Java one, like Java LangString, say. But it's all written using only juice features, right? So starting in assignment 2, you're always going to be compiling a whole bunch of classes, and that's going to include all the classes in this standard library. And you can find a copy of the standard library in the same place as the Marmoset test cases in the course account on the CS Linux servers. So you can download a copy of that standard library. Okay, and Marmoset will also give your compiler the standard library for all the tests starting in assignment 2. Okay, so string is some a class declared in the standard library. Okay, then I have method M, parameter B, that's a Boolean. Okay, Y, I have a use of Y. So what does Y refer to? And I look around here and there's no Y's. Well, there's this Y and there's this Y, but this Y can't be referring to either of these because these are in, within blocks. So which Y is this referring to? Well, oh, maybe it's this one. No, okay, it's this Y, right? So this Y is referring to this declaration, and that declaration is in a different class in a different file, right? But the compiler has to figure out, when I say Y here, well, there's at least 4 Y's or 5, I don't know, 4 Y's in this program that it could refer to, and it has to figure out when I say Y, I really mean this thing, right? This declaration or this identity, this concept, that field over there. Okay, and okay, why was it this Y? Well, because B extends A, and class A is here, so this field ends up being visible inside class B. All right, so B here, I think this one's pretty easy. It can only really be that parameter here, that parameter B. Okay, but now I declare a Y, and so this Y, which Y should this be? Well, it's the closest one. What about X? Oh dear, okay. So there's no X's here, so I need to go to the superclass. So this X is actually, this X over here. Okay. And now I go and I create a class, or I create an object of a class. The class is called B. Which class is it? Well, it's this one, but you can imagine I could have something more complicated here with packages or classes from other files or whatever. Okay, and I call a method M. And all right, so M, so I go for the closest thing, and I go for this M. Is it this M? Anyone? Does this M refer to this M? It seems like it, like, hey, that's the only M I see here. Yeah. Well, so actually, I don't know yet. I need to actually first figure out what this Y refers to, all right? So this Y, again, there's like 4 Y's here. So which Y is this? Well, it's the closest Y. And the closest Y is this one. Okay? So this Y is this Y. So what about M? Right? What does this name M refer to? Okay. So I've got no comments. So either everyone is puzzled or something. All right. So M is A.M. Okay. Yes. So M actually refers to this method M. Even though the closest method M is over here, but in Java we have method overloading, like in many other languages, and the idea is that inside this class B, we can have multiple methods M that have the same name, but just have different signatures, different parameter types. So this one takes a Boolean. This is a method M that takes an integer, and it's still visible in the subclass. So at this point, you can refer to both of these methods M. And the reason we choose this one is because this Y here has type int, and this is the method M that takes an int, while this is a method that would require a Boolean. So if this Y was actually, this Y instead of this Y, then this would refer to this method M. But because this Y is this Y, which is an int, this M actually refers to this M. Okay, so hopefully it's starting to become clear that this is not as trivial, right, as what we had here. Like, hey, it's X, so it's got to be that one. All right. So there's going to be a lot of work for the compiler to do here. Okay, and then finally, almost finally, we have string. So that's another reference to Java Lang string. And now we say, y equals y plus z. So the y's are these closest y's. The z is the only z, and also the closest z. So this one here. And there's one more thing I want to mention here. Here there's the plus, and the plus is a built-in operator, but sometimes the plus means add two integers, and sometimes the plus means concatenate two strings, right? So it has two different meanings, different operations, and those operations depend on how we're going to resolve these names, right? If these y's and the z were not strings, but say ints, then the plus would mean something completely different. Okay, and I've got, all right. So, I've got a good question from Yashin. So the question is, does name resolution work at runtime or at compile time? So in this case, I'm talking about compile time name resolution. So what the compiler is going to have to do to figure out, when it sees like a string, right, like X or Y or B, like what concept that that name actually refers to. And even in the case of M, there is a static meaning to the M. So this M, from the compiler's point of view, not even thinking about runtime, this M actually refers to this method M and not this method M, even statically. So for example, in this case, both of these return void, but if they had different return types, then the type of this overall expression would be determined by the M that this refers to at compile time. So there's a compile time notion of what a name means. There's also a separate runtime notion, and we'll get to that when we do code generation, right? So in code generation, we're going to generate the code that at runtime is going to figure out which method to actually call, and that in object-oriented languages or in functional languages, which nowadays is pretty much any language has either object-oriented or functional aspects to it. So most languages will have some sort of dynamic runtime resolution of what method code we will actually be executing. But we're going to deal with that later. For now, it's just the compiler assigning a meaning to each use of a name. Okay, yeah, good question. So thanks. Other questions? Okay. Yeah. So casting would be providing a hint to the compiler for the intended type. So that's a bit of a loaded question. Well, I mean, okay, right. So here, yes. So I could use a cast to force a particular overloaded method to be selected. I think that's the context of the question. I think in general, I could interpret that question in various ways. But if that's the idea, then yes. So the cast, a cast is an expression that has a specified type, and so that's one way to select a particular overloaded method. Yes, yes. All right, and we'll see more about casts later on. Okay, so all right, so how is the compiler going to do name resolution, right? So the main sort of data structure we're going to have. Oh no, my marker is dying, and I think my other black one died too. Well, okay, I guess it sort of kind of still works. So an environment, we're going to use environments, is a map from names to declarations. So the declarations, I mean the AST nodes, right? We talked about abstract syntax trees last time. So the idea is I'm going to have like some hash map or some other implementation of a map data structure that's going to take the maps. That's going to take the names, which are just strings, right? Right, like X and Y and A, to AST nodes. It doesn't have to be AST nodes. The point is I want to map the names to some data structure that represents the identity of a concept, like a field or a method. So I guess the key word here is identity, right? What I really want to know is that, say here, that the variable that I write to here, this y, is the same variable that I read from here, right? But it's a different variable than the one that I read from here. So I want to have an identity for each concept in my program, okay? And in terms of implementation, one form of identity is the AST node of the declaration, right? If each concept is declared exactly once in your program, which is the case for Java, is not the case for some languages. Like some languages allow you to just start using variable names without declaring that variable, and so in that case you wouldn't really have an AST node to link those uses of variables to. So you could create some other data structure in your compiler to represent a variable. But the point is, you need something that represents the identity of some concept. And the AST node of its declaration is one possibility, but you can also just keep the AST as a separate thing, and then introduce new objects or new data structures to represent each class, each method, each variable, and so on. Okay, but so the environment maps strings to their meanings, their identities, those concepts. And the idea is that we're going to have multiple environments, and we're going to have one environment for each scope. And so a scope is an area of the program. So area of program in which a declaration is visible, right? Or you could say in which a name is visible, right? And I mean, you've probably seen scopes before. Oh no, my screensaver. Okay, I got to figure out how to disable that. Okay, so you've probably seen scopes before, right? So the idea is that, for example, I'm going to have a scope for the entire class A. So the inside class A, I'm going to have a scope, and let's say I'll call it A, and the idea is that all the names that are within the class, so the fields and the methods, are visible inside this scope, right? So anywhere inside here, I can say things like X and refer to that field X, right? And all right, and I can have other scopes inside that scope. So for example, I can put a scope here, and I'm just going to call this one C, because I'm going to call this one B. Okay, so I can have another scope here, and so the scopes can be nested, right? And sort of the general concept is that when I'm looking for a name, I'm going to be looking in the most deeply nested scope. Okay, and so the idea is that each scope has its own environment. So each scope has its own environment. All right, so, and let's see. So has own environment. Okay, and it's an area of the program, and so I would associate it with some AST node. Okay, so for example, the class scope here, I would attach it to the AST node for the class, and sort of anything in the subtree of the parse tree that is rooted at this AST node can see the declarations in this scope, right? And this scope here, where you can see the parameter y would be attached to the method AST node. Okay. All right, so more scopes. So for the class B, we would have a scope where you can see things like the field Z, say, and then M, the method M would have a scope. I think I called it D. Yep. All right, let's call this one D. And then, each time I create a block, that creates a new scope in Java as well, right? And so I'll call these E and F. All right, and so these scopes are nested, right? So I've got B, and then D is nested inside B, and then E and F are nested inside D. So the scopes are nested, and I always use the lowest most or most nested scope. And so these scopes for these blocks, that's what allows me to distinguish this string y from the int y. Okay, and in terms of the nesting of the scopes, conceptually, I can say that the B scope is nested inside the A scope, I mean, it's a sort of, maybe a different form of nesting in that it's a subclass. It's not actually syntactically, the class B is not a nested class of A. It could be a nested class of A, but it is a form of nesting in that inside class A, I can still access the names. Sorry, inside class B, I can still access the names from class A. Okay, and then I've got scope C nested inside scope A. So, so scopes are nested. And so typically in a scope, you would have a pointer to the enclosing scope. So the outer, scope. Okay, because, let's say I'm in scope E and I'm looking up a name, and if I don't find it there, I want to look outwards in D and B and A and so on. Okay, so I often need a pointer to that outer scope, so going up this scope nesting tree. Okay, so you've probably seen these informally before. All right. So, okay. So I want to erase the example. So any questions or comments or thoughts about the example before I erase it? 5, 4, 3, 2, 1. All right. Anything? Can I erase it? Okay. Okay, so we're going to we're going to use these nested scopes to look up names, and name lookup. And the key to name lookup is you look in the most nested scope, and if not found in current scope, recursively search outwards. Okay, and maybe this is obvious, but why? So why did I write it down? Well, I want to contrast this with when I declare a name. So when I see a declaration of a name, like say here, I see a variable y being declared, right? So I'm going to give an error if the name exists in current scope. And the key here is I only look for the name in the current scope, right? So when you're implementing your compiler, one temptation might be to say, oh, I'm going to do the name lookup for that name. And if that name already exists, I'm going to give an error. But the name lookup actually goes to the outer scopes. And here you don't want to go to outer scopes, right? You want to allow, okay, and I erased it, right? But you want to allow to declare, say, the name y, even though there was already a y in scope in some scope that was further out, okay? But you want to make sure that you don't have duplicate names in the same exact scope. So if I have a y here, if I had another declaration of y, I would give an error. Okay, so that's a sort of a difference between looking up a use of a name and declaring a name. Okay, and there's one more general concept before we sort of look at how we're going to implement all this stuff, and that concept is namespaces. Okay, so let's look at namespaces. So here's a little Java example. So I can declare a field named X, and then I can declare a method also named X, and give it a parameter. I guess I could have even named this parameter X as well, just to make it. And the method has a body, and then I can say something like X equals X of X. Okay? So, how am I going to resolve these names here? And all right, well, it turns out that, this X is the field X, and this X is also the field X, but this X refers to the method X. Okay, and how, first of all, why is this even allowed? But okay, it is the Java allows it, and and how am I going to resolve these two different X's? Right, we're in the same scope, right? They're in the same place, but and so, if I look at my environment and I look up the name X, as a string, it's going to give me some AST node. Should it give me the method declaration or the field declaration? Yeah, I don't know, right? So there's really, two different X's in the same scope. One is a method and one is a field. Okay, and so the way that namespaces work is that you syntactically, so from the grammar, you figure out that, this X comes before an open bracket, so it has to be the name of a method, whereas, these other two X's don't come before an open bracket, so they're not method names, they're what Java calls the expression namespace, but they're basically names of variables, right? Or they could be names of fields. Okay, so based on where the name appears in the grammar, that's what decides which namespace to look in. And then, implementation-wise, we actually need a separate environment for each namespace. So, in each scope, we're going to have a separate environment for each namespace. Okay, so we'd actually have two environments, so two maps, one for methods, one for fields. And, for this X, we would look in the method environment and find a pointer to the method AST node. For this X, we would look in the expression one. All right, so all right, so the namespace is determined syntactically. So, and how many namespaces do we need? Well, it depends on the language, and Java is especially I'm trying to think of a good word here. Especially messy, I guess. or Java has more namespaces than many other languages. And so Juice sort of follows that. All right, so Java and Juice have 4 namespaces. So you actually, might need up to 4 environments in each scope. And so the 4 namespaces are package. There's some places where you're expecting the name of a package. The second namespace is called a type. And the Java spec really abuses the name type. It uses the name type to mean a class or interface, which is confusing because it also has a type system and type checking and things that are not just classes and interfaces. And we'll talk about types in general later on, but in the Java spec, they use the word type to mean class or interface. So there's some places where you're looking for the name of a class or an interface, and that's a separate namespace from packages. And then there is a namespace for methods that we've seen already. And then there's a namespace for expressions. Okay, so before, and so expressions just means variables and fields and stuff. All right, so when you see a name, before you can start looking for it in an environment, you have to figure out what namespace it's in. And then look in the appropriate environment, and that will lead you to the AST node, and that's how you will know what that name actually means. Okay, and so the namespaces are determined syntactically. So based on where your name appears in the grammar, except, right, it's Java, so it has to make things complicated. Except there is a position in the grammar where the spec says, oh, that's the ambiguous namespace, and then there's a whole algorithm that it gives you for deciding the namespace of a name that syntactically appears in a position that is associated with an ambiguous namespace. Okay, so this is, in theory, you're supposed to be able to tell syntactically, but in a real language like Java, things get complicated. I just want to give a reference to the language spec section 651, where you can read about namespaces in full detail. Okay, so I think I've given you an overview of the concepts that we are going to need to deal with. So now let's sort of look at what do we actually do, right? And I hope that at the beginning of the lecture, you thought, oh, this is easy, right? You see X in your program. Well, obviously, that means the variable X over here. And it's not that simple. And so now let's see, what are we going to do, right? All right, but I've got a question. So is this why Java can use dot for class and expressions, such as class A dot static field and instance dot field? But for C++ and Rust, you have to use like a double colon and a dot. I see. So yeah, so C++ and Rust would distinguish class names or the class namespace syntactically, but Java sort of abuses dot, right? It uses a dot for a lot more things, and it is precisely that dot that leads to the ambiguous namespace where if you see a dot in Java, you don't really know whether the thing before a dot should be in the expression namespace or I guess in this example, in the type namespace. But in C++, you would know, right? Because you would use a dot if it's expression, and you'd use colon if it's type, right? And I mean, I don't actually know how many namespaces C++ has. I mean, it probably doesn't have. Well, I don't know. I mean, C++ keeps changing out from under me, right? I was going to say it probably doesn't have packages, but it has. Well, it has a thing called a namespace, which is not the same namespace as what we're talking about here. So, okay. Yeah, I get, I don't want to get into C++ because that's going to just confuse things even more. But the point is, namespaces are these sort of categories of names where you can have names that coexist in the same scope, and they're decided based on where they appear within an expression. Okay. And that's not 100% true. In Java, you also have to do this extra algorithm, but conceptually, it should be possible to look at the grammar and figure out, a name that I see here, is it the name of a method or of a variable? Okay. But yeah, I do know that Scala only has 2 namespaces, right? Even though it's a lot closer to Java, and other languages will have other numbers. Sometimes languages will distinguish them by some other methods, like syntactic methods. So, for example, in ML and Haskell, the capitalization of a name, tells you what the name means, right? So types like have to be capitalized, and variables can't be capitalized, and stuff like that. Okay, so how are we going to do all this name resolution stuff, right? How are we going to link uses to their declarations? So name resolution in Java and in Juice. Okay, and so, I mean, this part is Java specific, but the same kinds of concepts come up in other languages. All right, so I'm going to give you, an easy 7-step process, all right, that you can implement. So the first step is we're going to build a global environment. All right, and so this is just the set of all classes. So all classes. All right, basically we run through the program and we make a list of all the classes. So this step is actually, easier than the others. Then as step 2, we're going to resolve type names. Okay, and by type names, I mean the Java spec thing of type. So class and interface names. So we're going to run through our program, and whenever we see something that has to be the name of a class or an interface, like say in that extends clause in my example, or after the new, again in the example, that has to be the name of a class or interface. And so we're going to figure out which one it is. Okay, after we know that, we're going to check the class hierarchy. Or I guess I should say the type hierarchy, to include interfaces as well. And this part includes figuring out methods and fields of classes. Okay, and so it's all about figuring out which methods and fields are available in each class. Okay, once we know, where the methods and fields are, and we've made sure that, there's, say, no cycles in the extends and implements relationships of classes and interfaces, then we can go to step 4. So we're going to deal with this ambiguous namespace. So disambiguate the ambiguous namespace. All right, so all those weird names that appear in places where you syntactically can't figure out what they are, here there's a little algorithm that does disambiguate, and a bunch of rules that say, okay, if you follow the rules, this name over here that you didn't know what it was before, well, now it's an expression, or now it's a type, or whatever. Okay, so then step 5, once we know that, but by now we know the namespace of every name. So here we're going to resolve. So any name that's in the expression namespace. Okay, and so this is specifically going to be local variables and static fields. Okay. Once we've done that, we can do type checking. All right, and so type checking is a whole separate, big can of worms, or another big topic. Just like name resolution is a major topic, type checking itself is a similarly major topic. But before you can do type checking, you have to do all this other stuff, right? You have to resolve all these names, but also, before you can finish name resolution, you need types. So you need type checking here. So finally, step 7 is to resolve methods. And so methods here are names in the method namespace and instance fields. Okay, so instance is sort of a word that means non-static. Okay, so if I see the name of a non-static field, I can't figure out which field it is until after I've done type checking. Okay, so the reason for these steps is that name resolution and type checking are interdependent. Okay, so type checking depends on name resolution. Name resolution depends on type checking. In Java and in pretty much every other modern programming language as well. Okay, they are presented as separate concepts, but almost everywhere they're interdependent. Okay, and in many languages, they're interdependent in really messy and complicated ways. I work with Scala a lot, and there, all of this is really one big, gigantic jumble of code that does name resolution and type checking, and it's all really deeply interdependent. For Java, they are interdependent, but you can kind of split them up into steps that you can do in sequence, these 7 steps. And, even though overall it's interdependent, if you do this first, then this, then this, then this, you can do them one at a time. Okay, so that makes it slightly easier in terms of implementing this. You can implement, each of these one step at a time. And in terms of the course, we're going to take these 3 steps, and they're going to be assignment 2, And then these 4 steps are going to be assignment 3. Okay, so I should mention assignments 2, 3, and 4 are smaller than, are each smaller than assignment 1 was. And the reason that they're separate is that, it's possible to separate them. Like, I guess I could have separated this really into 7 assignments instead of 2. But, each step can be done independently. On the other hand, with scanning and parsing, with scanning and parsing, depending on how you design your scanner and your parser, it's harder to separate them. So that's why they're one big assignment. Okay, but for assignment 2, we need to do these three steps. So let's look at those steps first. Okay, so sort of in more detail. Right. And again, questions, stop me, right? Okay, so for step 1, step 1. So the global environment. So, there's not really much to say here other than we have to run through the entire program and make a set of all class names. And we want the full name, including package name. Okay, and I put it as a step because you have to do it first, but it's really trivial. You just, look through all your code, find all the classes, attach each class name to the package that's declared in that same file, and you put these in a set, and now you have a set of all your classes. Okay, there's really nothing much else to do there. So, okay, that was way too easy, and we can go to step 2. Do ask questions if there's questions, but really, it really is that easy for step 1. The other steps are harder or longer. Okay, so we want to resolve type names. All right, I have it over here, so I won't write it again here. So we want to resolve type names. This is discussed in section 6.5. So you can go there for the details. But Java actually makes this easier than many other languages. So Java distinguishes qualified type names. And qualified just means that there's a dot in the type name, right? So like, A.B, let's say .C. But as long as there's at least one dot in the type name, it's a qualified type name. And in Java, when you see a qualified type name, it's easy. That must be the full name of the type. Okay, so you have to, you have to put the full name starting from the package name and the outermost package name, and as soon as you see a dot, the name has to be that full name. So you just look in your global environment and you find a type with that full name, and that's your type. Okay. And the hard case is a simple type name, and simple just means there's no dot in it. So it's like A, right? And now you have to figure out which class or which class it is. So for a simple type name, if there's not a dot, then it's not so easy. But I want to say, in many other languages, if you have a qualified name, that doesn't automatically make it easy, right? If a type name has a dot in it, well, and it looks like let's say A.B.C. Typically, you would first resolve A as something, and it might be a package or it might be a class or something, and you would resolve it in some complicated way, which is what we're going to do for a simple type name, and then within whatever A means, you would look for a B. Okay, and you'd have this iterated process. Scala does it that way. Pick any other language that has names that are separated in this way, and typically they will do it. C++ will do it that way, right? But Java, makes at least this part easier. As soon as you see a dot, you stop everything else and you say, well, I just need a outermost package called A with a package called B nested inside it, and then it's class C inside that nested package B, and that's it, and there's nothing more you have to do. Okay, so if I see a simple type name, right? If I in a place where I expect a type and I see A, right? Or we had our class B extends capital A, so I see the capital A, and I need to figure out which class A it is. Okay. Well, so there's a whole algorithm in the Java spec, so you can see it here, but I'll summarize it here. And there's 4 steps. So the first step is it the enclosing class or interface? Okay. So, let's say I see the expression new A. The first thing I do is I check to see whether that expression new A appears within a class named A. And if it does, then that A refers to exactly that class. Okay, and that's step 1. Step 2 is a single type import. So this is the name of a Java thing. So a single type import. So if you say, import A.B.C.D at the beginning of your file, and then you see the name D being used in that file, and there is an import with this name, then step 2 says it's class A.B.C.D, right? That's the class that it determines. Okay, and these rules, you follow them one by one, and the first one that works is the one that you take. Okay. So step 3, a type in the same package. Okay, so let's say I'm in package foo, and I see the name D, and there's no import for it. So I'm going to look for a class called D inside the same package that I'm currently in. Okay. Sorry, is 1 enclosing a substep under 2 qualified? Got confused about the ordering. Okay. All right. Yeah, no, I should. So all of this is for simple names, and qualified names are easy, and you don't have to do anything. Okay. So all these rules here are if I see a simple name, which means a name that there's no dot in it, it's just like an identifier, right? Like A. Okay. So if I ever see a dot, I'm doing this. But the point is, you know, if this A was not A but D, but that file has an import a.b.c.d, then the class that simple name D refers to is this class that I imported. Okay. If the import fails, I look in the same package for a type of that name. Right? So I look for, let's say, a type of named D or a type named A in the same package that I'm currently in. And finally, step 4 is an import. So again, Java calls it an import on demand package. I'll just say PKG, and that's an import with a star. So if I say, you know, import a.b.c.star, okay, so, you know, after I've looked for the class or interface with the same name in the same package, and I don't find it there, then I look at all these imports that say, you know, here's a package. I want to import all the names in that package. So sort of as a last resort, I look in all these imported packages. And these rules take precedence over each other. So there's precedence between rules. So rules 1 to 4. So you take the first one that works, but within one of these 4 rules, it has to be unambiguous, right? So if there's any ambiguity within one of these, then that's an error. So oops. So ambiguity within a rule is an error. Okay, and I mean you wouldn't have that in 1 or 3, I guess, but in the imports, right? You could have say 2 different packages that have a type with the name that you're looking for, and if that happens, then that would be an error. Okay, and one other thing here that is a warning, so sort of a common misconception, right? So in Java, at the top of your file, you put a package declaration, but you don't have to, right? The package declaration is optional. And if you don't put a package declaration, then your class goes into something called the unnamed package. Okay, so that's if your class file, if your file doesn't have any package declaration, you just start writing a class to begin with. And you might expect or it's sort of natural to think that the unnamed package is like the root package, like a package with an empty name, but it's not. Okay, so the sort of the warning here is that the unnamed package is not the root package. So in other words, if let's say I create a class C and I don't give it a package declaration, then I can refer to class C from within other classes in the unnamed package, right? I can have a class D that refers to class C, but it's impossible to refer to class C from a file in some other package or from a class in some other package. Okay, so let me cannot refer to types in unnamed package from any named package. Okay, so, well, why? Well, let's say, so I create a class C and it's not in any package. So, what is its full name? Well, its full name is just C, right? If I was to put it in a named package, then its full name would be the package name with possibly some dots in it or subpackages, .c. But if it's in the unnamed package, then its name is just C. And then the rules here, so, if I try to refer to it from a named package, well, I have to say just C. I can't say package.c because there is no package, right? It's in the unnamed package. And so I can't write it as a qualified type name because there's nowhere to put the dot. I'd have to just say C for class C. And so then it goes through these rules of a simple name. And, if I'm referring to it from another package, then it's not the enclosing interface. There's no way to import the unnamed package. And, it can't be a type in the same package if I'm in a named package, but the type was declared in the unnamed package. Okay, so there's kind of, when you go to implement this, there's a temptation to think, if there's no package declaration, that must mean I'm in like the root package or, a package that whose sort of string of package names is like the empty string. But that's not the case at all. And sort of the way, at least the way that I implemented the unnamed package in my compiler is to actually treat it as a named package, but give it some name that has some funny Unicode characters in it, or some characters that can't ever appear in any real name, so that you don't refer to it by accident. Okay, but the point is, it's not the root, right? It's if you think of a class with no package declaration as being in like some package that's the super package of all the other packages, that's wrong. That's not how the spec works. Okay, so be careful about the unnamed package. All right, and I thought I had one more thing about right. So the other thing about Java that's sort of maybe less of a misconception, but also sometimes a thing is so a package and its subpackages have no actual relation to each other, other than where they're supposed to be in the file system in a Java program. But there's no relation between, so no relation between, say, package A.B and say A.B.C. Okay, so you take each full package name, and this is a package and this is a package, and I mean in the spec they talk about them being this being a subpackage of each other, but there's no significance to being a subpackage. They're just two completely separate packages, as if they were, say, A.B and C.D, right? There's no connection between a package and a subpackage in Java. Okay, so keep these things in mind. These are kind of quirks of Java, but for resolving type names, and again, type names are the ones where syntactically they appear in a place where you expect the name of a type, like in an extends clause or in after a new. So here's how you figure out which class or interface that name refers to. Okay, so now we've done steps 1 and 2, right? You build the global environment, you resolve the type names. So those should be the first two things that you do for assignment 2. And we still need to do the class hierarchy. So there's going to be a bunch of things to do there to figure out which classes extend other classes and subclasses, subinterfaces, and which methods and fields are visible in each class and interface. So we will do that in the next lecture. But the next lecture will be the Monday after reading week. So next week is reading week. So enjoy it. I mean, I realize that with the pandemic and everything, it's not really any different than any other week. But it is different in that there are no lectures. So for this course and presumably any other course, there's no deadlines for assignments. You are welcome to keep working on the assignments, right? But there's no deadlines for the assignments. And the status meetings that we've been having on Thursdays. So we will have those tomorrow, right? Thursday. But there's no status meetings in the Thursday of reading week. And then we'll come back on the Monday after reading week. We'll have a lecture. We'll finish off this step 3, figuring out the class hierarchy, and then we'll be done with assignment 2, and we can continue on to these steps for assignment 3. Okay, so are there any final questions about anything before we break for reading week? I know it's going to be a long time. I'm going to forget all about this course. I am going to be on Piazza, right? So if you don't want me to forget all about the course, feel free to ask questions on Piazza. So if you need help, you can contact me, but there's no sort of scheduled lectures or assignment deadlines or meetings or anything. Okay, so any questions? All right, so have a good rest of this week. Have a great reading week, and I look forward to seeing you again on that Monday after reading week. Okay, bye.